All right, welcome back to round two. All right, so last time we talked about orbital notation and showing everything with energy levels, sublevels, orbitals, and arrows to represent electrons, right? And so what we're going to do today is we're going to take that same thing and we're going to take some assumptions, right? And we're going to make it easier to write, but also that means we have to understand what we're doing a little bit better. The nice part about orbital notation is everything's there. If you understand that, you got it. But today, with the three methods that we're going to take a look at now to make it even more simple, there's also things you have to understand in order to make sure you got it right. All right. And so electron configuration is built the same way as orbital notation, right? We start at the beginning and we build up, right? We use off bow. Okay. The problem is all of a sudden we get rid of the arrows and the lines. So we get rid of the knowing exactly where the electrons are and exactly what sublevel or exactly what orbital they're in, which makes it easier, but also we have to know what's going on in order to ensure we know exactly what atom we're talking about, right? So we have superscripts now. So we're gonna use numbers, which is why we're not gonna have to draw these out. We can do them pretty easily on our computer to represent electrons in the orbitals. Okay, and within the sublevel is probably actually a better way to say that. Okay, so here's an example. We've been using sodium, and so if I look at sodium, instead of having all those lines and arrows, right, I just have numbers. So what we're talking about, those electrons are right here. Okay. And if I add these up, I get to sodium, right? Which is a good check. Now, that doesn't mean you got it right, but a good check is adding up all these superscript electrons and saying, hey, I got 11. All right, that means I'm sodium. But we also got to make sure we built it right. So we start at 1s, and then 2s, and then 2p, and then 3s. So again, we're reading across our periodic table from left to right, top to bottom, right? And I got 1s2, 2s2, 2p6, 3s1. Okay, that is pretty easy. So what that would have been is I would have an up arrow and a down arrow and an S, an up arrow and a down arrow and an S. I had three orbitals here, so I had three up arrows and then three down arrows. And then here I would have had one up arrow. Okay, that is what we're running into. And so we got to think about this. What rules are we assuming? Okay, without having the orbitals and without having the arrows, out of our three rules, what rules are we assumed are being applied correctly? Okay. Now, what we should be thinking of is because we don't have arrows, right? It's really the Pauli exclusion principle in Hund's rule. If we don't know what direction they're going in this, and we don't know exactly what orbital they're in this, those are the two rules that we're assuming are correct. All right. So this is what, again, electron configuration can look like. Here's just a quick look at it. So we have the energy level, we have the orbital or the sublevel, all right, and then the number of electrons in that orbital. So really, in this case, with this one, it doesn't matter if we think of this as a sublevel or an orbital, because they're kind of one and the same at this point, because we're not breaking it out the same way that we did in orbital notation. Okay, so it makes it a little bit easier. So let's let's try these guys out. And I'm going to do it this way. I'm going to get out of presentation mode. Okay. Let's make this. Can I make this bigger? Let's see. Let's zoom out to 200. Oh, no, that's too big. All right. So right now, let's do this. So carbon. I have to start at the beginning. I got to build up. So I'm always going to start with a 1s, right? And what I know about carbon is I need 6 electrons. So that's useful. So I'm going to do 1s, and then I'm going to put a superscript of 2 because s's can always hold 2. All right, I'm going to move on. And so I went from hydrogen to helium, and now I'm down at lithium. So lithium is a 2s. Okay, so right now, if I'm looking at my periodic table, right, I'm down here at my 2s. And that means S's again can only have 2. And I'm going to put not a 4. Geez, thinking ahead. All right. So that means right now I have drawn in 2 more electrons for a total of 4. Right. So right now I have 4 electrons. And I'm going to go over to my 3s, or is it my 2p? Well, because it's based on energy, I'm going to go to my 2p. How many more electrons I need? I need 2. Now, a good way to check this is if you go to your 2p, right? Is carbon, where am I at? Is carbon the second one over? it is. All right, that's a nice quick check. I have 6 electrons. I'm 2 over in my 2p, and I'm done. Okay, so let's go to fluorine. The nice part about doing these on your computer instead of doing them on paper, which some of you complain about, is I could do this: copy, paste. Fluorine's bigger, so all I need to do is start here. All right, I already built up. As long as I built up correctly, I need to go to fluorine. Well, fluorine is still in my 2p, but it is now the 5th element over, and so I can do that. Pretty nice, right? It makes doing these problems fairly nice. All right, let's do phosphorus. Same thing, build up 1s2, 2s2, 2p, right? So I'm going to copy paste that in there. And now, because I'm going past this, that needs to become a 6, right? And that's the most electrons that a p can hold. If p's have 3 orbitals, right, and 2 electrons can be in each orbital, it can only hold a maximum of 6. So what I run into next, all right, is 3. I run into 3s, right? And if I go across 3s, I'm not in the 3s's, so I'm going to be 3s2. And then I would run into a 3p, right? And my 3p would be, if I'm phosphorus, I'd be 3 over, so I'd be 3p3. Okay, again, if I count all of these up, I should be at 15, and I am. Again, pretty nice when we're doing it that way. All right, let's go. I'm going to copy this guy, go down to manganese. All right, we're getting a little bit bigger, so I should probably change my font a little bit. Size of my font, let's go there. Let's drop it down to like 36 maybe. Good. All right, so manganese. Okay, manganese is all the way down here. It's element number 25, right? So I'm in my D block, which is one that we always want to do. Okay, so I'm going to go all the way through my 3p. So that means I have 6 elements there, or 6 electrons. And then I'm going to run into my 4s. Okay. From there, my 4s's are filled. So I'm going to put a 2 there. And then I run into my, what comes next? You're right, 3d. Okay, it's not 4d, it's 3d, because remember, the d's are always one number less. Now they're here. This isn't where they would be energy-wise. Energy-wise, they'd be in front of the 4s, but they're after the 4s because we're still basing this off of the number of electrons. Now, so that 3d, we want to remain there because we have them in the correct sequence. But energy-wise, we still only have 2 electrons in the valence shell because of that 4s2. So here, how many electrons do I have? If you count over, I have 20 up to this point, so that means I need 5 more. All right. And finally, bromine. Let's take this guy, and let's come down here. We'll paste it in there. Bromine is really big. All right, so it's going to go all the way through the D's. So D's can hold up to 10 electrons. Next, I come back to my 4p. Remember that. So after 3d comes 4p. And again, the periodic table shows you this. That's what I want you guys to realize, right? The periodic table shows you this, and you should be pretty good with that. Now, if we count over, I would be element number 5 in my 4p. And if I added all these up, I better have 35, and I do. So hopefully that starts to make some good sense for you, because if you can draw the orbital notation, this just gets easier. We just take some assumptions. We assume that we know what the electrons are doing with the arrows. Okay? All right. Let's move on. Let's go back to, let's not do presentation. Let's just do it this way. Can we see this well, though? All right. So noble gas configuration, okay, this is the same as electron configuration, but even easier. And by easier, we have to write less, all right? And it's called noble gas configuration because we start with a noble gas. And the noble gas we start with is always the one that is you would have ran into just before you would have hit the element, right? And so we'll do a bunch of example problems, and I'll be able to explain this better when we run into that. But basically, the noble gases, right, is on the right side of the periodic table. So we're looking anywhere from helium to radon over here. We're going to be using one of those guys to start, and then filling out the rest. Okay. So if we start with the noble gas coming before the element in the bracket, and then we build, why can we start with the noble gas? What do we know about noble gases? Well, what we know about them is they're completely filled, right? They're completely filled. And so because they're completely filled, we can say, hey, here's kind of like my core. I know I'm a noble gas. I know I'm filled. And then we can just build the part that's not necessarily filled after. So it's taking our electron configurations and just getting rid of some of it. And so you can see with sodium, right? Sodium is element number 11, right? So we are right here. And so all I would do is I'd go up a line, right? I go to period 2. I'd go to the noble gas in period 2, and that is neon. So I start with neon as my starting point. Hey, I'm at number 10, right? And then I start filling up the same way I would. So I go down to 3s and I fill that up. So rules assumed? Really, all the rules are assumed in this one. Because we got to assume that we understand that neon is already built up. Because if we only had a 3s1, that's not showing proper off-bow, right? So the thing about this guy is he is completely filled up. All right, so let's try our same problems out. Going to carbon. Okay, so carbon is in period 2. So that means we need to use the period 1 noble gas. The period 1 noble gas is helium. So we're going to just write helium, right? And for these small elements, this actually doesn't help us that much. But when we do really big elements, it'll help us out a lot, right? We have to write a lot more. So after helium, then I run into 2s, right? And that would be 2s2. And then I would run into 2p. And for carbon, it would be 2p2. So this didn't really save us at all, but it was slightly helpful. Let's do fluorine, right? Same thing. Fluorine would be He again, because fluorine's in period 2, so we go to the period 1 noble gas. And this is the same. So I'm just going to take this guy up here. All right, I'm going to copy it, bring it down here. All right, and I'm going to change this number. What should it be? Well, if you have your notes in front of you from the last one, it's the exact same number, right? This should be 2p5. Okay, so starting at helium, 2s2, 2p5. So really, helium, that's just the 1s2, right? That's all it's really giving us. Now, for phosphorus, it'll help us out even more because phosphorus started to get pretty big. So phosphorus is in period 3. So you got to look at period 3, and you got to go to the period 2 noble gas. So all of a sudden, not that, we're going to have neon, right? We have neon. Great. So neon is basically 1s2, 2s2, 2p6. So we don't have to write any of those. We could just start at 3s, right? Now it's not in the s's, so it's going to be 3s2. And we go over to the p's, and we'd have 3p. How many? 3. So you can start to see that using these noble gas configurations is actually going to help us out quite a bit as far as making this a little bit easier to deal with. Manganese, right? Let's go to manganese. So manganese is in period 4. So we would go and we would build from period 3. So this would be argon. Okay, and again, you don't have to memorize that. It's just part of your notes. And then we come down to 4s. Okay, make sure you're looking at your periodic table. 4s would be a 2. And then what do we need? We need our 3d5. And that's it. We got rid of everything else in front of it with just a bracket and our noble gas. And bromine is going to be even easier. All right, bromine, again, not easier, but it's a lot simpler than what we wrote down the first time. All right, so again, we have argon. Okay, and then we have 4s2. And then we'd have 3d, 10. And then we'd end with 4p. How many? Oh, not that. 4p5. Good. All right, that's it. Right, that's it. That is something that we can take a look at, and you are able to do. But again, we got to start with understanding the orbital notation that has everything in order to get down to this and understand, hey, there's a lot that's assumed here, but if I build it correctly, if I look at the periodic table, I'm good. All right. Next up then is going to be this guy, right? So the electron dot structure. So the nice thing about this guy is we get rid of a lot of stuff, right? All we really have is we have our symbol. We have 4 sides. Think of this as being a box. Okay. And we are assuming a ton of stuff. We assume that this guy has all of the inner electrons, all those electrons that are not considered valence electrons, right? The outermost electrons are there. Okay, so we're not even labeling. We're not even saying, hey, we know the inner electrons are there by showing some of them are having a noble gas. We're just saying, hey, man, they're all there. Don't even worry about them, right? We only care about the possibility of having 8 valence electrons. Okay, and so what we do is we have this box and we have 2 per side. Now, not all rules are assumed in this one. So remember Hund's rule. Hund's rule said you had to separate the electrons as much as you can. So when we do this, basically we have 4 sides and it doesn't matter where you start. All right, but you cannot double up a side until every side has at least 1. Okay, so in this case, sodium only has 1. Because it's got a 3s1. That's what that guy is. All right, but it doesn't have to have any more. Okay, so let's try a few of these out. We'll go back to this, and for this, I am going to actually do these on paper because it doesn't work as well on our computers. So a little bit here, and then we're done. So what we're going to do is we are going to take a look at carbon. Okay. And so carbon, what we want to know is how many valence electrons it has, right? We don't care about any of the other inside stuff. And so when we look at this guy, remember the D's and the F's have nothing to do with our valence electrons. So all we really need to know is at the outermost energy level, right? So in this case, at energy level 2, because that's where carbon's at, how many S's and P's do we have? Well, we have 1, 2, 3, 4. Now, we can get that many different ways. We can look at the periodic table, which is what I would like you to be able to do. We can also, if we built up from before, we can also look at that with our arrows. We can look at that by adding up the number of superscripts in either of the other 2 versions. But basically, I need to put 4 electrons around this guy. So again, you don't have to draw a box, but basically, this guy's got 4 sides. Using Hund's rule, saying we have to separate them, I don't care how you do this, but basically, we need to write in 4 electrons. And when we start building these, this is how carbon really works. So that's the answer. That is carbon, right? That is the electron dot structure for carbon. All right, let's take a look at fluorine. Fluorine is way over here. Again, it's an energy level 2, but it has to go how many more over? So we have carbon, we have 5 or 4 there, 5, 6, 7 more. All right, and so with this guy, again, just start. Doesn't matter where you start. There's our 4 that we have from carbon. Now we have to add in 3 more. Doesn't matter where you put them, as long as in these orbitals, you only put in 2 extra, right? So we have 1, 2, 3, 4, 5, 6, 7, and we have this basically 1 open space right there, which is going to come in when we start talking about bonding, right? But that guy is the 7 valence electrons that we have for fluorine. Looking at phosphorus, right? It doesn't matter where phosphorus is. It's an energy level 2. If we look at it, it has 5 valence electrons. So again, we can just kind of go around our circle and we can place the electrons just like that. Okay. Not magnesium, manganese. All right. Manganese is a weird one. Why is manganese a weird one? Manganese is a weird one because it's right here, right? It's right there. So when we take a look at it based on its placement on here, how many valence electrons does it have? Well, this is where the D block doesn't do a great job. But basically, when we take a look at this row, how many valence electrons come before it? Well, because there's S's right here and it doesn't get to the P's yet, this manganese is only going to have 2 dots. Now, for these transition metals, that's oversimplified. We're not really going to do many dot knots with those. We'll deal with them more when we talk about bonding, but that's it. All right, bromine, same thing. It's a halogen. It's got 7 valence electrons. All right, it's got 2 S's and 5 P's. So we are just going to do this. And again, it doesn't really matter what it looks like as long as you have them in pairs and you have singles. All right. Hopefully that works out. We'll do some of these together tomorrow and